For as long as human civilization has existed, the night sky has served as both a map and a mystery. Across continents and cultures, early societies looked upward to find patterns, guidance, and meaning among the stars. These points of light appeared fixed, forming constellations that repeated their positions with predictable precision. They became markers of time, tools for navigation, and foundations for mythology. Yet not all lights in the sky behaved in the same way. Among the steady stars, a small number of celestial objects moved. Their motion was subtle, unfolding gradually over nights and months, but it was unmistakable. These objects wandered across the sky, following paths that did not align with the constellations. Because of this, ancient astronomers referred to them as wanderers. One of these wanderers stood apart from the others: Mars. Its distinguishing feature was its colour, a deep, reddish hue that set it apart from the pale, steady light of most stars. To the naked eye, it appeared almost like a glowing ember suspended in the darkness. This visual difference ensured that it was noticed, recorded, and interpreted by nearly every civilization that observed the sky. In ancient Rome, the planet was named after Mars. The association was not arbitrary. The reddish colour evoked blood, fire, and conflict, qualities closely linked to the nature of war. The name reflected both the appearance of the planet and the cultural meanings attached to it. This interpretation was not unique to Roman society. In ancient Greece, the same planet was associated with Ares, another deity of war. In Mesopotamian traditions, Mars was linked to Nergal, a god connected with destruction and plague. In ancient China, it was known as the fire star, representing chaos, disruption, and transformation. These independent associations, formed in societies separated by vast distances and limited communication, reveal a shared human tendency to interpret the unknown through familiar symbols. The reddish light of Mars inspired similar meanings across cultures, suggesting that its visual impact was both immediate and universal. Beyond its colour, Mars also exhibited behaviour that distinguished it from other celestial objects. Unlike the fixed stars, which maintained their positions relative to one another, Mars shifted its location over time. Its path across the sky followed a slow arc, occasionally pausing and even reversing direction before continuing forward again. This phenomenon, now understood as retrograde motion, was particularly puzzling to ancient observers. Without knowledge of heliocentric models or orbital mechanics, this backward movement appeared irregular and unpredictable. It challenged early attempts to impose order on the heavens. Some cultures interpreted this motion as a sign of instability or unrest, reinforcing the planet's association with conflict. Despite these uncertainties, early astronomers began to track Mars with increasing precision. Babylonian records, some of the earliest known astronomical documents, include detailed observations of planetary motion, including that of Mars. These records demonstrate a shift from purely symbolic interpretation towards systematic study. By observing Mars over long periods, ancient scholars were able to identify patterns in its movement. They noted its cycles, its periods of brightness, and its changing position relative to the stars. These observations laid the groundwork for future advancements in astronomy. In ancient Greece, philosophers and astronomers sought to explain planetary motion through geometric models. The geocentric system, which placed Earth at the centre of the universe, required increasingly complex mechanisms to account for the observed behaviour of planets like Mars. Epicycles, small circular motions superimposed on larger orbits, were introduced to explain retrograde motion. While these models were ultimately incorrect, they represented an important step in the development of scientific reasoning. They demonstrated an effort to reconcile observation with theory, even when the available framework was limited. For centuries, Mars remained an object of careful observation, but limited understanding. Its distance prevented any direct insight into its nature. It remained a point of light, distinctive, but fundamentally unresolved. At the same time, its presence in the sky was constant. It appeared in different seasons at different positions, but it never disappeared entirely from human awareness. Generations of observers watched it rise and set, chart its course, and assign it meaning. Empires rose and fell beneath its steady glow. Technologies advanced, languages evolved, and knowledge accumulated, yet Mars itself remained unchanged in appearance. This continuity contributed to its enduring significance. Mars was both familiar and mysterious. It was seen regularly, yet never fully understood. It invited observation, but resisted explanation. This combination ensured that it remained a focal point of curiosity across centuries. As time progressed, the methods used to study the sky became more refined. Observations grew more precise, records more detailed, and theories more sophisticated. The transition from myth to measurement was gradual, unfolding over generations rather than moments. A major turning point came with the work of astronomers such as Nicholas Copernicus, who proposed a heliocentric model of the solar system. In this framework, the Sun, rather than Earth, occupied the centre, and the planets, including Mars, orbited around it. This model provided a simpler explanation for the motion of Mars, including its retrograde behaviour. Instead of requiring complex systems of epicycles, retrograde motion could be understood as a natural result of the relative positions and velocities of Earth and Mars as they moved around the Sun. Later, Johannes Kepler refined this understanding by demonstrating that planetary orbits were not perfect circles, but ellipses. His laws of planetary motion describe the relationship between a planet's distance from the Sun and its orbital speed, offering a more accurate model of celestial mechanics. Mars played a crucial role in these discoveries. Kepler's work was based in part on detailed observations of Mars made by Tycho Brahe. The irregularities in Mars's motion, which had once been a source of confusion, became key evidence supporting a new understanding of the solar system. In this way, Mars contributed not only to mythology and observation, but also to the development of modern astronomy. Despite these advances, the physical nature of Mars remained largely unknown. Even with improved models of its motion, it was still seen only as a distant object. Its surface, atmosphere, and composition were beyond the reach of observation. This limitation would persist until the development of new technology. The invention of the telescope in the early 17th century marked the beginning of a new phase in the study of Mars. For the first time, it became possible to observe the planet with magnification, revealing details that had previously been invisible. This transition from naked eye observation to telescopic study would transform Mars from a point of light into a visible world. The red glow that had inspired myths and questions for millennia was about to take on form and structure. Mars would no longer be just a wandering star, it would become a place. And with that transformation, the nature of the question surrounding it would change as well. No longer limited to interpretation and speculation, humanity would begin to ask more specific, more scientific questions. What does Mars look like? What is it made of? Does it resemble Earth in any meaningful way? These questions would guide the next phase of exploration. The red light in the ancient sky had done its work. It had inspired curiosity, observation, and inquiry across countless generations. It had shaped myths, influenced science, and contributed to a growing understanding of the universe. Now, as new tools emerged and new methods developed, that curiosity would take a more focused form. The study of Mars was about to enter a new era, one defined not by distant observation alone, but by the pursuit of detail, structure, and physical reality. The wandering light would become a world. The transformation of Mars from a distant point of light into a tangible world began with a quiet technological shift, one that did not announce itself with spectacle, but gradually altered humanity's relationship with the cosmos. The invention of the telescope in the early 17th century marked a turning point in observational astronomy. For the first time, celestial objects could be studied with magnification, allowing details to emerge where previously there had been only suggestion. When Galileo Galilei directed his telescope toward the night sky, he revealed a universe far more complex than had been imagined. The moon displayed mountains and shadows. Jupiter was accompanied by orbiting moons. Venus showed phases much like the moon. The heavens, once thought to be perfect and unchanging, were suddenly revealed to be dynamic and structured. Mars, too, was transformed by this new perspective. Through early telescopes, it appeared not as a sharp point, but as a tiny disk. Though the image was still small and often blurred by the limitations of early optics, the implication was profound. Mars was no longer an abstract light. It had dimension. It occupied space. It was, in every meaningful sense, a world. This realization shifted the nature of inquiry. Rather than asking what Mars represented, astronomers began to ask what it was. Over the following decades and centuries, improvements in telescope design gradually enhanced the clarity of planetary observations. Larger lenses, better polishing techniques, and refined mounting systems allowed astronomers to observe Mars with increasing detail. Subtle variations began to emerge on its surface. Observers noted that certain regions appeared darker while others were lighter. These markings were not static. They seemed to shift slightly over time, influenced by seasonal changes or atmospheric conditions. The presence of bright polar caps, visible at the top and bottom of the planet, suggested the accumulation of ice, which appeared to grow and shrink with the Martian seasons. These observations hinted at a world that was not entirely inert. Mars seemed to possess cycles, patterns that changed over time. The polar caps suggested freezing and thawing. The darker regions, though not fully understood, appeared to expand and contract in response to these seasonal variations. To many observers, these features made Mars feel familiar. It was not identical to Earth, but it shared certain characteristics: rotation, seasonal change, and surface variation. These similarities encouraged further speculation. If Mars had seasons, perhaps it had weather. If it had weather, perhaps it had an environment capable of supporting life. Such questions remained speculative, but they were increasingly grounded in observation rather than myth. In the 19th century, the study of Mars entered a more detailed phase. During favourable oppositions, periods when Mars and Earth were relatively close, astronomers could observe the planet with greater clarity. These windows of opportunity allowed for more precise mapping and documentation. Among the most influential observers of this period was Giovanni Schiaparelli. In 1877, during a particularly favourable opposition, he conducted extensive observations of Mars and produced detailed maps of its surface features. Schiaparelli identified a network of linear markings, which he referred to as canali. In Italian, the term described natural channels or grooves. However, when translated into English as canals, it suggested artificial construction. This distinction, subtle but significant, altered the interpretation of his observations. The idea that Mars might contain canals implied the presence of intelligent beings capable of engineering large-scale structures. This interpretation quickly gained attention, extending beyond the scientific community into popular culture. One of the most prominent advocates of this idea was Percival Lowell. Convinced that the canals were real and artificial, Lowell dedicated much of his life to studying Mars. He established observatories, produced detailed maps, and proposed a comprehensive theory of Martian civilization. According to Lowell, Mars was an aging world. Its water resources were diminishing, and its inhabitants had constructed an extensive network of canals to distribute what remained from the polar regions to the equatorial areas. This system, he argued, represented a desperate but sophisticated attempt to sustain life on a dying planet. Lowell's ideas captured the imagination of the public. Mars was no longer just a world, it was potentially inhabited. It became a subject of fascination not only for scientists but also for writers, artists, and the general public. The possibility of life beyond Earth, once a philosophical question, began to feel tangible. However, not all astronomers agreed with Lowell's conclusions. Many struggled to confirm the existence of the canals using their own observations. The linear features were often faint and difficult to discern, leading to inconsistent reports. Some observers saw them clearly, while others saw nothing of the kind. As telescope technology continued to improve, the evidence for canals became increasingly uncertain. By the early 20th century, it became clear that the canals were not physical structures, but rather optical illusions. The human brain, when presented with faint and ambiguous visual data, tends to organize it into patterns. In this case, subtle variations in shading were interpreted as continuous lines. The canals, though not real, had a lasting impact. They demonstrated the interplay between observation and interpretation. They highlighted the limitations of human perception, particularly when dealing with distant and poorly resolved objects. Most importantly, they fueled a sustained interest in Mars that would persist even after the canal hypothesis was abandoned. While the idea of advanced civilizations on Mars began to fade, the question of life did not disappear. Instead, it evolved. Scientists began to consider simpler forms of life, microorganisms that might exist under conditions very different from those on Earth. This shift reflected a broader understanding of biology, including the discovery of extremophils on Earth, organisms capable of surviving in environments once thought to be uninhabitable. At the same time, scientific measurements provided a clearer picture of Mars's environment. Spectroscopic analysis revealed that the planet's atmosphere was composed primarily of carbon dioxide, with very little oxygen. Atmospheric pressure was found to be much lower than that of Earth, making it unlikely that liquid water could exist on the surface for extended periods. Temperature measurements indicated a cold world, with average surface temperatures well below freezing. These conditions suggested that Mars, in its present state, was not conducive to complex life as it is known on Earth. Yet certain features remained intriguing. The polar caps, for example, were confirmed to consist of ice, partly water ice, partly frozen carbon dioxide. Seasonal changes in these caps suggested active processes, even if limited in scope. The darker regions on the surface, once thought to be vegetation, were reinterpreted as areas of exposed rock or dust. Mars was revealed to be a dynamic planet, but one operating under conditions very different from those of Earth. By the mid-20th century, the limitations of telescopic observation had become apparent. Even the most powerful Earth-based telescopes could not provide the level of detail needed to fully understand the Martian surface. A new approach was required. Rather than observing Mars from a distance, scientists began to consider the possibility of sending instruments directly to the planet. This idea, once the domain of speculative fiction, became increasingly plausible with advances in rocketry. The development of powerful launch vehicles during and after the Second World War laid the foundation for space exploration. What had once been theoretical began to take practical form. Mars, which had been observed for thousands of years, was now within reach. The transition from observation to exploration represented a fundamental shift. Instead of interpreting faint signals from afar, humanity would begin to collect direct data. Images, atmospheric readings, and surface measurements would replace speculation. This shift marked the beginning of a new era. Mars would no longer be defined solely by what could be seen through a telescope. It would be studied through instruments placed in its orbit, and eventually on its surface. The world that had once been a red light in the sky had become a subject of detailed scientific inquiry, and soon it would become something more, a destination. As the study of Mars became more precise, the boundary between scientific observation and human imagination remained unusually porous. Even as telescopic data began to correct earlier misconceptions, the planet continued to inspire visions that extended far beyond what instruments could confirm. Mars occupied a unique position in human thought. It was close enough to observe in detail, yet distant enough to remain largely inaccessible. This combination allowed uncertainty to persist, and within that uncertainty, imagination continued to grow. During the late 19th and early 20th centuries, the concept of life on Mars became one of the most compelling ideas in both science and culture. The earlier interpretations of surface markings, particularly the controversial canal hypothesis, had already laid the foundation for imagining Mars as inhabited. Even as scientific confidence in those interpretations weakened, the broader idea of extraterrestrial life remained deeply influential. At the centre of this period of speculation was the belief that Mars might represent a world similar to Earth, but older and more environmentally strained. The notion suggested a planet that had undergone gradual desiccation, losing its surface water over vast spans of time. Within this framework, any hypothetical Martian civilization would not be thriving under ideal conditions, but rather adapting to decline. This concept resonated strongly with thinkers and writers of the era. It offered a reflection of Earth's own vulnerability, framed within an alien context. Mars became a kind of mirror, one that allowed humanity to project both its aspirations and its anxieties onto another world. Among the most influential works to shape public perception during this period was The War of the Worlds by H.G. Wells. In this narrative, Mars was not a passive or dying world, but the origin of a technologically advanced species capable of interplanetary travel. The Martians depicted in the story were highly intelligent, physically distinct from humans, and equipped with machinery far beyond contemporary human technology. Their arrival on Earth was portrayed not as a diplomatic encounter, but as an existential threat. The narrative emphasized vulnerability, imbalance, and the limits of human preparedness. The impact of this work extended beyond literature. It influenced scientific curiosity, public imagination, and cultural discourse about the possibility of extraterrestrial intelligence. Mars, through fiction, became associated not only with life, but with power and technological superiority. In 1938, the boundaries between fiction and perceived reality were briefly disrupted during a radio adaptation of the story. Presented in a format resembling breaking news, the broadcast led some listeners to believe that an actual Martian invasion was underway. The programme, narrated by Orson Welles, demonstrated how persuasive narrative structure could temporarily override critical interpretation, particularly when delivered through familiar media formats. Although the reaction was limited in scale and often exaggerated in later retellings, the event underscored the enduring psychological impact of Mars-related narratives. Even as scientific understanding advanced, the symbolic power of Mars remained strong. At the same time, scientific perspectives on life beyond Earth were undergoing a gradual transformation. Rather than focusing on advanced civilizations, researchers began to explore the possibility of microbial life. This shift reflected a growing awareness of the diversity of life on Earth itself, particularly the discovery of organisms capable of surviving in extreme environments. These findings expanded the definition of habitability. Life, it appeared, did not require conditions identical to those found on Earth's surface. Instead, it could persist in environments previously considered inhospitable, such as deep ocean vents, frozen tundra, and highly acidic or alkaline systems. This broader biological understanding influenced how Mars was evaluated. Instead of asking whether complex life might exist on the surface, scientists began to consider whether simpler forms of life could have emerged in the planet's past or persisted in protected environments beneath its surface. This shift in perspective aligned with emerging geological evidence. Increasingly detailed observations suggested that Mars had not always been the dry, frozen world observed in modern times. Surface features resembling dried river valleys, outflow channels, and sedimentary formations indicated that liquid water had once been present. These formations implied a fundamentally different ancient environment. At some point in its history, Mars may have possessed a thicker atmosphere, higher surface pressure, and conditions that allowed water to remain stable on the surface for extended periods. If such conditions had existed, even temporarily, the possibility of microbial life became more scientifically plausible. Despite these developments, direct evidence of life remained absent. no definitive biological signatures had been detected, and Mars continued to resist easy classification. It was neither clearly lifeless nor demonstrably inhabited. This ambiguity sustained scientific interest. As the 20th century progressed, technological advancements began to shift the focus from Earth-based observation to direct exploration. Rocketry, developed significantly during and after the Second World War, enabled the possibility of sending instruments beyond Earth's atmosphere. What had once been speculative discussion gradually became engineering challenge. The idea of reaching Mars transformed from abstract possibility into a defined objective. Missions could now be designed, planned, and executed with specific scientific goals in mind. This transition marked the beginning of a new phase in planetary exploration. Mars was no longer confined to telescopic study or theoretical modelling. It would soon be approached directly, measured by instruments travelling across interplanetary space. The long era of interpretation was approaching its end. In its place, a new era was beginning, one defined by data, measurement, and encounter. Mars, once a symbol in the night sky, and later a subject of speculation, was about to become a destination for machines built on Earth. And with that transition, the nature of human understanding of the planet would change permanently. By the middle of the 20th century, Mars had already been observed for centuries, yet it remained fundamentally unchanged in human experience. Every understanding of the planet had been constructed indirectly, through light collected by telescopes, filtered by distance, atmosphere, and the limitations of human perception. Mars was known only through interpretation, never through contact. That situation began to shift as technological development during the early space age made it possible for human-made objects to leave Earth entirely. The emergence of rocketry introduced a new capability: controlled motion beyond Earth's atmosphere and gravitational influence. This development did not immediately enable interplanetary travel, but it established the foundation upon which such travel could eventually be built. Early rocket systems were unstable, often unpredictable, and difficult to control with precision. Yet each improvement in propulsion, guidance systems, and structural engineering expanded the range of what was possible. As these technologies matured, Mars gradually became a realistic target for exploration. However, reaching Mars required more than simply building a powerful rocket. It required an understanding of orbital mechanics at a level of precision never before necessary in human engineering. Both Earth and Mars move continuously along their own orbital paths around the Sun. As a result, a spacecraft launched toward Mars cannot travel in a straight line. Instead, it must follow a carefully calculated transfer orbit that accounts for the motion of both planets over time. These launch windows occur only once approximately every 26 months, when the relative positions of Earth and Mars allow for the most efficient transfer trajectory. Even within these windows, mission planning is constrained by fuel efficiency, travel duration, and the ability of onboard systems to function independently over long periods. During the journey, communication between Earth and spacecraft is not immediate. Depending on orbital alignment, signals can take anywhere from several minutes to over 20 minutes to travel one way. This delay makes real-time control impossible, meaning spacecraft must be capable of executing pre-programmed instructions without intervention. In the early stages of Mars exploration, this combination of distance, delay, and limited computational power created extraordinary technical challenges. The first wave of missions launched toward Mars in the 1960s reflected both ambition and limitation. Several early attempts failed to leave Earth orbit or lost communication shortly after launch. These failures were not unusual given the state of technology at the time. Rocket reliability was still developing, and interplanetary navigation required levels of precision that were difficult to achieve consistently. The Soviet Mars program conducted multiple early missions, many of which experienced launch failures or communication losses. Each unsuccessful attempt, however, contributed to a growing understanding of the engineering requirements necessary for deep space exploration. Problems related to staging, thermal control, and guidance accuracy were identified and gradually addressed through iterative design improvements. Despite these setbacks, progress continued steadily. In 1965, a critical milestone was achieved with the launch of Mariner 4 operated by NASA. This mission represented the first successful attempt to reach Mars and return scientific data from its vicinity. Unlike orbital missions, Mariner 4 was designed as a flyby spacecraft. Its trajectory would carry it past Mars at a relatively close distance before continuing into heliocentric orbit. This approach reduced the complexity of orbital insertion while still allowing for close-range observation. As Mariner 4 approached Mars, anticipation among scientists was significant. For decades, Mars had been associated with theories of canals, seasonal vegetation, and even possible civilizations. However, the reality of the planet's surface remained unknown at close range. The spacecraft's imaging system began transmitting data as it neared the planet. However, the transmission process was extremely slow by modern standards. Each image was encoded into a sequence of data points, sent across millions of kilometers, and reconstructed on Earth through careful processing. The first images arrived in fragmented form, requiring gradual assembly. As the data accumulated, a consistent picture began to emerge. The surface of Mars appeared heavily cratered, resembling ancient lunar terrain. There were no visible signs of large-scale geological reshaping, no apparent river systems, and no evidence of surface water in liquid form. The landscape suggested a world that had remained largely unchanged for immense spans of time. This result had a profound impact on scientific understanding. Long-standing speculative models that imagined Mars as Earth-like or inhabited were no longer supported by observational evidence. Instead, Mars appeared to be a geologically inactive planet at its surface, with a history shaped primarily by impact events rather than erosion or biological processes. However, rather than diminishing interest in Mars, this discovery redirected it. If Mars was not currently Earth-like, then the question shifted to its past. Scientists began to consider whether the planet may have experienced different environmental conditions earlier in its history. The cratered surface suggested long-term stability in its current state, but did not rule out earlier periods of geological activity. Following Mariner 4, additional missions were launched to refine and expand these findings. Mariner 6 and Mariner 7, launched in 1969, provided higher resolution imaging and more detailed atmospheric measurements. These missions confirmed that Mars possessed a very thin atmosphere composed primarily of carbon dioxide. Surface pressure was found to be less than 1% of Earth's atmospheric pressure, making the presence of stable liquid water on the surface highly unlikely under current conditions. Temperature readings reinforced this conclusion. Mars exhibited extreme cold, with average surface temperatures well below the freezing point of water. Daily and seasonal variations occurred, but overall conditions remained hostile to Earth-like life. Despite these findings, subtle variations in surface features continued to attract scientific attention. Differences in brightness, seasonal changes in polar ice caps, and localized atmospheric activity suggested that Mars was not entirely static. A major advancement occurred with Mariner 9 in 1971, which became the first spacecraft to enter orbit around another planet. Orbital insertion represented a major engineering achievement. Unlike flybys, which provided only brief observational windows, orbit allowed continuous monitoring over extended periods. This enabled the study of seasonal changes, atmospheric dynamics, and surface evolution over time. When Mariner 9 arrived at Mars, it encountered an unexpected condition, a global dust storm that enveloped the entire planet. The surface was completely obscured, preventing immediate observation. Rather than terminating observations, mission controllers maintained orbital operations while waiting for the storm to subside. This decision extended the mission duration and demonstrated the importance of persistence in space exploration. Over time, the dust gradually settled, revealing the Martian surface in unprecedented detail. What emerged fundamentally changed the scientific perception of Mars. Massive volcanic structures were discovered, including Olympus Mons, a shield volcano of extraordinary scale. Its height and width exceeded any known volcanic feature on Earth, indicating prolonged and intense volcanic activity in Mars's geological past. In addition, extensive canyon systems were identified, most notably Valles Marineris, a vast network of interconnected valleys stretching across thousands of kilometers. The scale of this system suggested tectonic and erosional forces operating over extremely long periods. Perhaps most significantly, Mariner 9 revealed branching valley networks resembling dry riverbeds. These formations strongly indicated that liquid water had once flowed across the surface of Mars. This discovery represented a major shift in planetary science. Mars was no longer understood as a uniformly inactive world. Instead, it was recognized as a planet with a complex geological history, one that included periods of significant surface activity and environmental conditions potentially capable of supporting liquid water. This reinterpretation had far-reaching implications. If water had existed on Mars in the past, then the possibility of past habitability became scientifically plausible. Even if the planet was now cold and dry, it may not have always been so. This realization fundamentally redirected future exploration goals. Rather than focusing solely on current surface conditions, scientific inquiry began to prioritize the reconstruction of Mars's environmental history. Understanding how and when the planet transitioned from a potentially warmer, wetter state to its current arid form became a central objective. The era of direct exploration had fully begun. Mars was no longer an abstract point of light or a telescopic disk. It had become a physical world, mapped in increasing detail by machines that had crossed interplanetary space to reach it. And yet, even these discoveries represented only the beginning of a far more detailed exploration that would follow. By the mid-1970s, Mars had already been studied longer than almost any other planet beyond Earth. Centuries of telescopic observation had mapped its seasonal changes, its polar caps, and its shifting surface markings. Earlier spacecraft had finally broken the boundary between observation and proximity, sending back close-range images that revealed a cratered ancient world. Yet even after all of that progress, Mars remained fundamentally indirect in human experience. It had been seen, measured, and modelled, but never truly entered. The scientific question that emerged from this limitation became increasingly clear over time. It was no longer sufficient to understand Mars as an object in space. The next stage required understanding Mars as an environment. That meant direct interaction with its surface, its atmosphere at ground level, and its soil chemistry and real physical contact. Every prior mission had observed Mars from above or from a passing trajectory, but none had touched it. This gap between observation and contact defined the next major step in planetary exploration. To bridge it required a machine capable of surviving a sequence of conditions that had never been attempted on another planet. The spacecraft would need to enter the Martian atmosphere at extreme velocity, endure intense heat generated by compression and friction, slow itself using aerodynamic resistance, and then complete a controlled descent to the surface. Once landed, it would need to operate autonomously for extended periods, conducting experiments without real-time instructions from Earth. This was not a single engineering challenge, but a chain of interdependent systems. Each phase of the descent depended on the success of the previous one. A failure in heat shielding would end the mission during entry. A failure in parachute deployment would cause uncontrolled descent. A failure in landing propulsion would result in impact. And even after landing, the system would still need to function in an environment that was cold, dry, and chemically unfamiliar. This complexity led to one of the most ambitious planetary programs ever developed, the Viking mission, led by NASA. The Viking program was designed with dual objectives. The The first was to obtain high-resolution images of the Martian surface from orbit. The second, far more challenging objective was to place landers directly on the surface and conduct in situ scientific experiments. These two components worked together. Orbiters provided global context, while landers provided local physical reality. The engineering design reflected this dual structure. Each Viking mission consisted of an orbiter and a lander. The orbiter would remain above Mars, mapping terrain, tracking weather patterns, and relaying communications. The lander would detach, descend through the atmosphere, and become the first functioning laboratory on the surface of another planet. The descent process itself represented one of the most precise sequences ever attempted in space exploration. As the lander approached Mars, it would first enter the upper atmosphere at interplanetary velocity. At this stage, a heat shield protected it from the extreme temperatures generated by atmospheric compression. The surface of the shield would glow with energy as it absorbed and deflected heat that would otherwise destroy the spacecraft. As the vehicle slowed, atmospheric drag would begin to take effect. However, Mars' atmosphere is extremely thin compared to Earth's. It is dense enough to create heat and resistance, but not dense enough to slow a spacecraft completely. This created a narrow operational window in which parachutes could be deployed. When the parachutes opened, they dramatically reduced velocity, but not enough to guarantee a safe landing. At this point, the spacecraft still retained too much speed for a passive touchdown. To complete the descent, retro-rockets were activated, firing downward to counteract remaining momentum. This final phase required extreme precision. The timing of ignition, the duration of thrust, and the remaining altitude all had to align perfectly. Even small deviations could result in catastrophic failure. The entire sequence occurred autonomously, as communication delays between Earth and Mars made real-time control impossible. In 1976, this complex system was tested for the first time at full scale. The first successful landing was achieved by Viking 1. Shortly afterward, its counterpart, Viking 2, also reached the surface safely. These landings represented a historic transition in planetary exploration. For the first time, a fully operational scientific laboratory had been established on another planet's surface. Mars was no longer only observed, it was physically engaged. The initial images transmitted from the surface revealed a landscape that was immediately striking in its familiarity and alienness simultaneously. The ground was composed of reddish soil, broken by scattered rocks of varying sizes. The horizon appeared flat and distant, under a sky that carried a faint but perceptible tint, caused by suspended dust in the atmosphere. Light on the Martian surface behaved differently from Earth. It was softer, less intense, filtered through a thin atmosphere dominated by carbon dioxide. Shadows were visible, but not sharply contrasted. The overall visual impression was one of quiet stillness, as though the planet had entered a long period of inactivity. Yet despite this apparent stillness, the environment was not entirely inert. Subtle movements of dust were detected across the surface, driven by weak winds. These winds did not resemble Earth's dynamic weather systems, but they were sufficient to shift fine particles and gradually reshape small surface features over time. Temperature measurements reinforced the image of a harsh environment. Mars experienced extreme cold, with temperatures regularly falling far below the freezing point of water. The thin atmosphere provided almost no insulation, allowing heat to escape rapidly after sunset. As a result, temperature fluctuations between day and night were severe. Atmospheric analysis confirmed earlier orbital data. The atmosphere was composed primarily of carbon dioxide, with trace amounts of nitrogen and argon. Oxygen was nearly absent. Surface pressure was less than 1% of Earth's atmospheric pressure, meaning that liquid water could not remain stable under current conditions. The soil itself became a central focus of scientific investigation. It appeared oxidized, giving it a reddish color consistent with iron-rich compounds exposed to long-term atmospheric interaction. This oxidation suggested a history of chemical processes that had altered the surface over time, even in the absence of active geological reshaping. Despite the environmental harshness, the Viking missions were not designed solely to study physical conditions. Their primary scientific objective was far more profound: to determine whether life existed or had ever existed on Mars. To address this question, each lander was equipped with a series of biological experiments designed to detect metabolic activity in soil samples. These experiments represented some of the most sensitive life detection instruments ever sent beyond Earth. Soil was collected using mechanical arms and introduced into controlled chambers. Within these chambers, the samples were exposed to nutrient solutions and chemically labelled compounds. The goal was to observe whether any reactions occurred that could be attributed to biological processes. One experiment measured gas exchange between soil and atmosphere. Another, known as the labelled release experiment, introduced radioactive nutrients and monitored for signs of metabolic consumption. A third experiment attempted to detect organic synthesis under simulated Martian conditions. When the experiments began, the results were initially ambiguous. Certain readings indicated unexpected gas release after nutrient exposure. These signals suggested that chemical reactions were occurring within the soil that might resemble biological activity. For a brief period, this raised significant scientific interest. The possibility that Viking had detected microbial life on Mars was considered seriously. However, as additional data accumulated, inconsistencies became apparent. Not all experiments produced the same results. Some showed no reaction at all. Others produced signals that could not be consistently reproduced. Further analysis suggested that the Martian soil contained highly reactive oxidizing compounds. These compounds were capable of producing chemical reactions that mimicked biological signatures without requiring any living organisms. This interpretation gradually became the dominant scientific conclusion. The soil was chemically active, but not biologically alive. Yet the results were not entirely dismissive of life. Instead, they introduced complexity. Mars was not sterile in a simple sense. It was chemically unusual in ways that complicated interpretation. The absence of confirmed life did not eliminate the possibility of past life or subsurface microbial ecosystems. Meanwhile, the orbiters continued to gather global data. They mapped atmospheric circulation, tracked seasonal changes in polar ice, and observed dust storms that occasionally expanded to planetary scale. These storms could envelop the entire surface, reducing visibility and altering atmospheric dynamics for extended periods. The presence of such storms revealed that Mars, despite its thin atmosphere, possessed global weather systems capable of significant environmental impact. By the end of the Viking missions, Mars had been fundamentally redefined. It was no longer imagined as a world of canals or civilizations. It was not a thriving Earth-like planet. Instead, it was understood as a cold, dry, chemically reactive world with a complex geological history and a present-day environment shaped by thin atmospheric processes and seasonal variability. Yet even with this understanding, the question of life remained unresolved. The Viking results did not confirm its presence, but they also did not fully eliminate the possibility of past habitability. Mars still held evidence of ancient river valleys and geological structures that suggested a very different past environment. The planet had been touched for the first time, its surface analysed directly, its atmosphere measured at ground level, and its chemistry tested under controlled conditions. But instead of providing final answers, the Viking missions expanded the scope of uncertainty. Mars had become more real than ever before, yet also more complex. It was no longer a distant symbol or a speculative world. It was a physical place with a layered history, only partially understood. And in that partial understanding, the foundation was laid for the next era of exploration, one that would send mobile machines across its surface, travelling through its terrain and extending human perception even further into the Martian landscape. After the Viking missions, Mars entered a long period in which exploration continued. but in a far more distant and observational way. The landers had provided direct contact with the surface, but they were fixed in place, limited to the immediate surroundings of their landing sites. The orbiters expanded global understanding, yet they remained high above the terrain, unable to interact with it physically. What was missing from Mars exploration was mobility, a way to move across the surface, to travel between geological features, to follow evidence rather than remain anchored to a single point. The planet had been seen from orbit and touched in isolated locations, but it had never been explored in motion. This gap led to the development of a new class of spacecraft, robotic rovers designed to traverse the Martian landscape. These machines would combine imaging systems, analytical instruments, communication arrays, and autonomous navigation software, all within a compact mobile platform capable of surviving the harsh Martian environment. Unlike landers, rovers would not study a single fixed location. Instead, they would extend exploration outward in gradual movement, turning Mars from a static observation site into a navigable terrain. The first successful attempt at this concept came decades after Viking, when advancements in computing, robotics, and materials science finally made sustained surface mobility possible. By this time, Mars had already been reshaped in scientific understanding. It was no longer viewed as a potentially Earth-like world, nor as a completely inert planet. It was understood as a complex geological system with a dry present and a wetter ancient past. However, much of its surface history remained unexplored at ground level. Orbiters had identified valley networks and mineral signatures suggesting ancient water activity, but no mission had yet followed those clues directly across terrain. That would now change. In 1997, a new era of surface exploration began with the arrival of the first successful Mars rover mission, deployed by Mars Pathfinder. The mission included a lander and a small rover named Sojourner. While modest in scale compared to later missions, Sojourner represented a critical technological breakthrough, controlled movement on another planet's surface. The rover was not large. It was roughly the size of a microwave oven, equipped with basic cameras and instruments designed to analyze rock composition. Its movement was slow and deliberate, advancing only short distances at a time. Yet even this limited mobility fundamentally changed the nature of exploration. For the first time, a machine was not confined to a single location on Mars. It could move toward rocks of interest, adjust its position based on findings, and extend scientific inquiry beyond a fixed radius. The terrain surrounding its landing site revealed a mixture of rounded rocks and sandy soil deposits, suggesting past interactions with fluid processes. Although water was not present in liquid form during the mission, the shapes and distributions of surface materials indicated that it may have played a role in the planet's geological history. Sojourner's mission demonstrated that mobility was not only possible, but scientifically valuable. Each movement allowed new measurements, new visual perspectives, and new interpretations of the landscape. However, Sojourner's operational range was limited. Its batteries, communication systems, and computational capacity restricted its lifespan and distance. It was a proof of concept rather than a full exploration platform. The next generation of rovers would need to go further, both literally and technologically. That next generation arrived in the early 2000s with two more advanced robotic explorers, Spirit and Opportunity. These twin rovers were part of the Mars Exploration Rover program, designed to investigate whether conditions on ancient Mars may have supported liquid water. Unlike Sojourner, these rovers were significantly larger, more durable, and equipped with advanced scientific instruments. Their mobility systems allowed them to travel across kilometers of terrain, climbing small slopes, analyzing rock layers, and investigating sedimentary structures. When Spirit landed in early 2004, followed shortly by Opportunity, expectations were carefully measured. Engineers anticipated missions lasting approximately 90 Martian days, known as sols. This time frame was based on assumptions about dust accumulation, mechanical wear and power limitations from solar energy systems. However, what followed exceeded all expectations. Opportunity in particular demonstrated extraordinary endurance. Instead of lasting months, it continued operating for years. It travelled across vast stretches of Martian surface, studying layered rock formations that revealed evidence of ancient water activity. These formations included mineral deposits that typically form in the presence of liquid water on Earth, strongly suggesting that Mars had once experienced wet environmental conditions. Spirit also contributed important findings, though its mission path was different. It explored regions with evidence of past volcanic activity and hydrothermal interactions, indicating that Mars had undergone multiple geological processes capable of altering its surface chemistry over time. Together, the twin rovers transformed Mars from a largely theoretical geological history into a mapped and studied surface environment. Each rock analysed, each soil sample examined, and each image transmitted added detail to the growing understanding of the planet's past. Layers of sediment suggested ancient lake beds. Mineral formations pointed to chemical interactions with water. Surface textures indicated erosion patterns shaped by environmental forces no longer active today. Mars, as revealed by the rovers, was not simply dry and inactive. It was a planet that had changed dramatically over time, transitioning from a wetter, potentially habitable past into its current cold and arid state. This realization reshaped the focus of planetary science once again. The question was no longer whether Mars had ever been Earth-like in appearance alone. Instead, the focus shifted toward understanding the duration and stability of its ancient habitable conditions. How long did liquid water exist? What kind of environment did it create? And most importantly, could it have supported microbial life long enough for life to emerge? As Opportunity continued its extended mission far beyond its expected lifespan, it became a symbol of persistence in planetary exploration. Its journey across the Martian surface spanned years, then decades in mission terms, far exceeding initial design expectations. Dust storms occasionally threatened its solar power system, sometimes reducing energy levels to critical thresholds. During such periods, the rover would enter low power modes, conserving energy until sunlight returned. Despite these challenges, it repeatedly recovered and resumed operations. Spirit, although less fortunate in later stages, also contributed valuable geological data before eventually becoming immobile due to terrain limitations and mechanical issues. Even in its stationary state, it continued to function as a scientific station for a time. The success of these rovers demonstrated the effectiveness of mobile exploration. Mars was no longer a series of isolated points of observation. It had become a landscape that could be traversed, studied in motion, and understood through continuous physical interaction. Yet even as these missions expanded understanding, they also revealed new layers of complexity. Mars was not uniform. Its surface varied dramatically from region to region, with differences in composition, history, and geological structure. Some areas showed clear signs of ancient water flow, while others appeared shaped primarily by volcanic or impact-related processes. This diversity suggested that Mars had experienced multiple environmental phases over its history, each leaving distinct geological signatures. The rovers had not only confirmed that Mars was once different, they had shown that it had been different in multiple ways, across multiple periods. As Opportunity continued its long journey, eventually travelling farther than any previous rover on another planet, it became clear that Mars exploration had entered a new phase. The planet was no longer being observed in isolated snapshots. It was being experienced as a landscape over time. And yet, despite all the progress made, vast regions of Mars remained untouched. The rovers had explored only small portions of its surface, leaving most of the planet still unknown at ground level. Beyond their paths lay cratered plains, massive canyon systems, ancient volcanic regions, and subsurface mysteries that had yet to be investigated directly. The rovers had opened the door to surface mobility. but they had also revealed how much remained beyond reach. Mars had become familiar in detail, yet still vast in unknown structure, and that balance between knowledge and mystery would define the next stage of exploration, where even more advanced systems would begin to investigate not just the surface, but the deeper history and potential habitability of the planet itself. By the time the next major rover mission reached Mars, the planet had already been redefined multiple times. It had been a wandering light in ancient skies, a telescopic disk with shifting markings, a cratered world revealed by early flybys, a landing site for stationary laboratories, and a traversable landscape explored by long-lived robotic rovers. Each phase had stripped away older assumptions while replacing them with more complex and precise understanding. Yet even after decades of exploration, one of the most fundamental questions remained unresolved in a deeper geological sense: whether Mars had ever sustained long-term habitable environments capable of supporting life, even at a microbial scale. The earlier rovers had already provided strong indications that liquid water had once been present. Mineral deposits, sedimentary layering, and erosion patterns all pointed toward a wetter ancient Mars. However, those findings were scattered across multiple regions and limited by the capabilities of earlier instruments. What was still missing was a more complete integrated understanding of ancient environmental conditions, something that could connect isolated clues into a coherent planetary history. This objective defined the next stage of exploration, embodied by a more advanced robotic system designed not just to move across the surface, but to reconstruct the environmental evolution of Mars in deep time. That system was the rover known as Curiosity rover, developed under the broader program of NASA. Unlike its predecessors, Curiosity was not simply a rover designed to identify interesting rocks or travel across terrain. It was a mobile laboratory built to investigate planetary habitability itself as a scientific system. Its instruments were designed to analyze chemistry at a molecular level, detect organic compounds, study sedimentary structures in detail, and evaluate whether ancient environments on Mars could have supported stable liquid water over extended periods. The landing of Curiosity in 2012 represented another major engineering milestone. The rover was significantly larger and heavier than previous missions, which made landing more complex. The atmosphere of Mars, while thin, still required careful deceleration management. Traditional parachutes alone were insufficient for such a mass, and so the descent system had to incorporate a highly controlled sequence of entry, parachute braking, powered descent, and final precision landing. This process culminated in the use of a rocket-powered descent stage often described as a sky crane maneuver. In the final moments before landing, Curiosity was lowered on cables from a hovering descent platform, allowing it to touch down gently while the propulsion system moved away to avoid dust interference. This sequence was executed autonomously, with all critical timing decisions pre-programmed due to communication delay constraints between Earth and Mars. The success of this landing demonstrated a new level of precision in interplanetary engineering. Once on the surface, Curiosity began operations within Gale Crater, a region selected not randomly but based on orbital evidence suggesting it once contained persistent water activity. The crater's central feature, Mount Sharp, appeared to contain layered sedimentary deposits that could represent long-term environmental changes, recorded over millions of years. This made the location scientifically significant. Rather than examining isolated rocks, Curiosity would traverse a geological archive, moving upward through layers that represented different periods of Martian history. From its earliest observations, the rover confirmed that the terrain was not uniform. The ground consisted of finely layered sediment, suggesting deposition in the presence of water. Some formations resembled ancient riverbeds or lakebed sediments, shaped by slow-moving or standing water rather than rapid erosion. These findings reinforced a growing scientific model that Mars in its distant past was not only wet, but capable of sustaining stable bodies of water for extended periods. As Curiosity moved through Gale Crater, it encountered increasingly complex geological structures. Some layers contained clay minerals, which on Earth typically form in neutral water environments that are favourable for chemical complexity. Other layers showed evidence of sulfate minerals, indicating shifts in environmental chemistry over time. This variation suggested that Mars had not experienced a single static ancient environment, but rather multiple environmental phases. At certain times, conditions may have supported relatively stable lakes. At others, the chemistry of the water changed, possibly becoming more acidic or evaporating entirely. The idea of a long-lived Martian lake system became one of the most important scientific interpretations of the mission. Instead of brief or transient water flows, Curiosity's findings suggested that liquid water may have existed in some regions for thousands or even millions of years at a time. This duration is significant in planetary habitability studies, because stable liquid water over long periods increases the probability that prebiotic chemistry, or even microbial life, could develop. In addition to geological analysis, Curiosity was equipped with instruments capable of detecting organic molecules. These carbon-based compounds are essential building blocks of life as understood on Earth. Their presence alone does not confirm biological activity, but they are a necessary component for life as it is known. During its exploration, Curiosity detected a variety of organic compounds preserved in ancient rock samples. These findings were particularly important because organic molecules are typically vulnerable to degradation under harsh radiation conditions. Their preservation suggested that parts of Mars' subsurface or sedimentary structures had once provided protection from environmental breakdown. This discovery reinforced the idea that Mars may have once been chemically suitable for life, even if no direct evidence of life itself was found. At the same time, Curiosity monitored atmospheric conditions, revealing that Mars continues to experience seasonal and chemical changes even in its present state. Methane fluctuations detected in the atmosphere became a subject of ongoing scientific interest, as methane on Earth is often associated with biological processes, though it can also be produced geologically. The source of these variations on Mars remained uncertain, contributing to an ongoing ambiguity in the search for life. The planet continued to present signals that were suggestive but not definitive. As Curiosity ascended the slopes of Mount Sharp, it effectively moved through time. Each geological layer represented a different era of Martian history. Lower layers corresponded to older, wetter environments, while higher layers reflected more recent, drier conditions. This vertical progression allowed scientists to reconstruct a long-term narrative of environmental transformation. Mars appeared to have transitioned from a planet with stable surface water to one dominated by arid and oxidizing conditions. The cause of this transition remained one of the central questions in planetary science. Atmospheric loss, reduced magnetic shielding, and long-term climate evolution were all considered contributing factors. Over time, Mars appears to have lost much of its atmosphere, reducing pressure and allowing surface water to escape or freeze. Despite these changes, evidence suggested that subsurface environments may still retain traces of ancient water or chemical activity. This opened new directions for future exploration, focusing not only on the surface but also beneath it. Curiosity's extended mission demonstrated that Mars was not simply a static archive of past conditions. It was a dynamic record of planetary evolution, preserving layers of environmental change in its geological structure. The planet was increasingly understood not as a single environment, but as a sequence of environments unfolding over time. Each phase left behind traces that could still be read millions or billions of years later. This realization shifted the scientific focus even further. The question was no longer only whether Mars had been habitable, but how long those habitable conditions lasted, how they changed, and whether any protected environments could have preserved biological signatures. As Curiosity continued its slow ascent through Mount Sharp, it became clear that Mars still held many unanswered questions. each discovery revealed new layers of complexity rather than final conclusions. The surface of Mars had become a record of deep planetary time, but it was still only a partial record. Beneath and beyond Curiosity's path lay vast regions yet to be explored, each potentially holding additional clues about the planet's history. And so Mars remained in a state of gradual revelation. Not a world that yielded answers quickly, but one that unfolded its history layer by layer, requiring persistent observation and patient interpretation. By the time the next rover mission was conceived, Mars had already been transformed into a layered scientific narrative. Orbiters had mapped its surface in global detail, earlier rovers had crossed its plains and hills, and Curiosity had revealed that at least some regions once contained long-lived lakes capable of supporting stable liquid water. The planet was no longer a mystery in the sense of being unknown in appearance. Instead, it had become a place whose history was partially readable, though still incomplete. What remained unresolved was not whether Mars had ever had water, but whether that water had created conditions suitable for life, and whether any traces of that possibility might still be preserved today. This question required a new approach. Earlier missions had demonstrated that Mars preserved geological evidence of its past, but accessing the most promising environments required a more precise landing strategy and a more targeted scientific objective. Rather than exploring broad regions, the next mission would focus on a specific ancient environment identified from orbit as one of the most promising candidates for past habitability. This led to the selection of Jezero Crater as the landing site for the next major rover mission, a region that appeared to have once contained a river delta flowing into a standing body of water. The geological structure of the crater suggested that sediments carried by water had been deposited in layered formations over long periods of time, potentially preserving organic material if it had ever existed. The mission was developed under the Mars 2020 program of NASA, and the rover itself was named Perseverance rover. Its scientific objective was more focused than any previous rover: to search for signs of ancient microbial life, and to collect and store samples that could eventually be returned to Earth. This concept marked a significant evolution in planetary exploration. Instead of relying solely on onboard analysis, Perseverance was designed to function as part of a long-term system of sample return. Rocks and soil would not only be studied in place but also sealed in containers and deposited on the surface for a future mission to retrieve and bring back to Earth laboratories. This would allow analysis with instruments far more sensitive than anything that could be carried on a rover. The landing of Perseverance in 2021 represented another highly complex engineering achievement. Like its predecessor Curiosity, it required a multi-stage descent through the Martian atmosphere. The spacecraft entered at high velocity, protected by a heat shield that absorbed extreme thermal energy generated by atmospheric friction. As it slowed, a parachute deployed to further reduce speed, though not enough to complete a safe landing. In the final phase, a powered descent system took control. Using a combination of radar and onboard navigation, the spacecraft identified a safe landing zone and executed a controlled descent. In the final seconds, a sky crane system lowered Perseverance to the surface using cables, while the descent stage moved away to avoid disturbing the landing site with rocket exhaust. Every step of this process occurred autonomously. The communication delay between Earth and Mars made manual control impossible during descent. The system had to interpret terrain, adjust trajectory, and execute landing decisions in real time. When Perseverance finally touched down in Jezero Crater, it became the most advanced scientific laboratory ever placed on another planet. The selected landing site immediately proved its scientific value. Jezero Crater displayed clear geological evidence of an ancient river delta. From orbit, layered sediment structures had already suggested water activity, but ground-level observation confirmed the complexity of these formations. The rover encountered fine-grained sediments, sandstone formations, and mineral deposits consistent with long-term interaction with liquid water. These materials were particularly significant because river deltas on Earth are among the most effective environments for preserving organic material. As sediments accumulate in slow-moving water, they can trap and preserve chemical and potentially biological signatures for millions of years. If life ever existed on Mars, such environments would be among the most likely places for its traces to remain. Perseverance was equipped with advanced instruments designed to analyze these materials at high resolution. It could examine rock composition, detect chemical signatures, and identify textures at microscopic scales. Each rock was not just photographed but interrogated for its geological and chemical history. Early findings confirmed that Jezero crater had once contained a stable lake environment. Sedimentary layering indicated deposition in calm water conditions, while mineral analysis revealed compounds formed in aqueous environments. These findings reinforced the growing scientific consensus that ancient Mars had been significantly wetter than its present state. As the rover continued its exploration, it began collecting core samples from selected rocks. These samples were carefully sealed in titanium tubes designed to preserve their internal composition. Each sample represented a potential snapshot of ancient Martian chemistry, locked away for future retrieval. This process introduced a new concept in planetary exploration: delayed analysis. Instead of receiving complete scientific answers immediately, the mission was designed to store potential evidence for future missions that do not yet exist. The full scientific return would depend on a future sample return mission still in development. Alongside its primary scientific instruments, Perseverance carried a secondary technological experiment that represented another major milestone in space exploration. This was the small autonomous helicopter known as Ingenuity helicopter. Ingenuity was not originally intended as a core scientific instrument. Its purpose was to test whether powered flight could be achieved in the thin atmosphere of Mars. The Martian atmosphere, being less than 1% the density of Earth's, presents a unique challenge for aerodynamic lift. Rotor blades must spin at extremely high speeds to generate enough lift to overcome gravity. When Ingenuity first deployed, expectations were modest. It was designed for a limited number of test flights, each demonstrating controlled takeoff, hovering, and landing. However, once activated, it quickly exceeded its original objectives. Its first successful flight demonstrated that controlled powered flight was possible on another planet. It rose into the thin atmosphere, hovered briefly, and returned to the surface. This moment represented a fundamental expansion of exploration capability. Subsequent flights extended range and complexity. Ingenuity began traveling between locations, capturing aerial images of terrain that rovers could not easily access. It provided a new perspective on Mars, revealing surface structures from above at low altitude and high resolution. What began as a technology demonstration evolved into a functional aerial reconnaissance system, assisting the rover by scouting terrain ahead and identifying potential scientific targets. Meanwhile, Perseverance continued its geological mission. It moved slowly across the crater floor, analysing rocks that contained layered sedimentary structures, mineral deposits, and signs of long-term water interaction. Each discovery reinforced the idea that Jezero crater had once been a dynamic aquatic environment. Some rocks displayed textures consistent with deposition in flowing water, while others suggested quieter lake conditions. Variations in mineral composition indicated changes in water chemistry over time, suggesting that the environment had evolved rather than remaining static. These findings contributed to a broader understanding of Martian climate evolution. Mars was increasingly seen not as a single environment that changed abruptly, but as a planet that transitioned gradually through multiple climatic states. At one point, it may have had stable rivers and lakes. Over time, these systems diminished as the atmosphere thinned and surface water became unstable. The preservation of geological layers within Jezero crater provided a record of this transition. Each layer represented a different stage in environmental history, potentially spanning millions of years. As Perseverance collected and stored samples, the significance of its mission extended beyond immediate analysis. It became part of a long-term scientific chain, one that would only be completed when future missions retrieve and return these samples to Earth. In that sense, the rover is not an endpoint, but a link in a longer process of discovery. Despite the progress made, no definitive evidence of past or present life has yet been confirmed. However, the conditions identified by Perseverance, ancient river deltas, lake sediments, and organic-bearing minerals, represent some of the most promising environments yet found. Mars continues to present a dual reality. It is both clearly a planet with a rich geological past and one whose biological history remains uncertain. Each mission reduces ignorance but expands complexity. The surface of Mars is no longer a distant unknown. It is a mapped, traversed, and analysed landscape. Yet beneath that familiarity lies a deeper question that remains unanswered. Whether, at some point in its ancient history, Mars was ever truly alive in even the simplest form, and that question continues to guide every new mission that follows. As Mars exploration progressed through robotic missions, a parallel shift began taking shape in human thought. The planet was no longer only a subject of scientific investigation, nor simply a distant world being gradually revealed by machines. It began to emerge as a potential extension of human civilization itself. This shift did not happen at once. It developed gradually through advances in rocketry, reusable launch systems, orbital engineering, and long-duration spaceflight research. Each improvement in access to space reduced the conceptual distance between Earth and Mars, not in terms of physical space, but in terms of feasibility. Mars had always been far in distance, but now it was becoming closer in planning. The fundamental idea that began to dominate discussions in space agencies, private industry, and scientific communities was no longer only about understanding Mars, but about reaching it with human presence. Robotic exploration had revealed enough about the planet to confirm both its challenges and its potential. The environment was extreme, a thin atmosphere dominated by carbon dioxide, surface temperatures frequently far below freezing, and radiation exposure significantly higher than on Earth due to the lack of a global magnetic field. Yet despite these conditions, Mars remained the most Earth-like planet in the solar system in terms of its day length, seasonal cycles, and surface accessibility. A Martian day, slightly longer than an Earth day, created a rhythm that human biological systems could potentially adapt to. Seasonal cycles, driven by axial tilt, produced recognizable environmental patterns. The presence of water ice at the poles and in subsurface regions suggested that key resources might exist in accessible forms. These characteristics transformed Mars from a purely scientific destination into a potential site for long-term human activity. Among the organizations most closely associated with this shift was SpaceX, which began publicly outlining long-term plans for human missions to Mars. These plans centered around the development of large-scale, reusable launch systems capable of transporting significant payloads beyond Earth orbit, including the possibility of transporting humans in sustained missions. The concept of human Mars missions introduced a new set of challenges far beyond robotic exploration. Unlike machines, humans require continuous life support, stable pressure environments, protection from radiation, and access to water, food, and breathable air. Every aspect of survival would need to be either transported from Earth or produced locally on Mars. This requirement led to increasing interest in the concept of in situ resource utilization, a strategy focused on using Martian materials to support human presence. The atmosphere, though thin, contains carbon dioxide that could potentially be processed into oxygen. Water ice, detected beneath the surface and at the poles, could provide drinking water and be separated into hydrogen and oxygen for fuel production. These ideas formed the basis of early conceptual models for Mars habitation. Rather than treating Mars as a place requiring constant resupply from Earth, future missions would need to function with increasing independence. At the same time, scientific understanding of Mars continued to evolve. Orbital data and rover missions had already confirmed that ancient Mars once contained liquid water in stable environments. This raised the possibility that subsurface regions might still preserve chemical conditions that could be relevant to past or even present microbial life. The idea of colonization therefore existed alongside a scientific caution. Mars was not an empty or inert world in the historical sense. It was a planet with a complex geological and potentially biological history, and any long-term human presence would need to account for planetary protection principles designed to avoid contamination of potential native environments. This created a dual framework for future exploration: expansion and preservation. Human activity on Mars would need to balance scientific discovery with ethical responsibility toward an environment that might still hold scientific or biological significance. As mission planning advanced, attention also turned toward the psychological and physiological effects of long-duration space travel. Unlike short orbital missions, travel to Mars would require months of transit time in confined spacecraft. During this period, crews would be isolated from Earth, exposed to microgravity, and dependent entirely on onboard systems for survival. Once on Mars, additional challenges would arise: reduced gravity, different atmospheric pressure, and exposure to cosmic radiation would all affect human health over extended periods. Every aspect of habitation would need to be carefully designed to mitigate these risks. Despite these challenges, the idea of human presence on Mars continued to gain momentum. It was supported not only by technological development, but also by a growing understanding of planetary history. Mars was no longer seen as an alien world in the absolute sense. It was a world that shared enough similarities with Earth to make sustained presence conceivable, even if extremely difficult. In parallel with these forward-looking ideas, robotic missions continued to refine knowledge of the planet. Orbiters mapped subsurface ice deposits, rovers analysed sediment layers, atmospheric studies tracked seasonal methane fluctuations that remained scientifically unexplained. Each new dataset added complexity to the planetary picture. Mars was simultaneously becoming more familiar and more mysterious. Familiar in its mapped structure and known conditions, but mysterious in its unresolved history and unanswered questions. One of the most significant conceptual shifts in this period was the recognition that Mars may once have been habitable for extended periods in its ancient past. Geological evidence from multiple missions suggested the presence of lakes, rivers, and possibly even stable hydrological cycles. These conditions may have existed long enough for prebiotic chemistry, or even simple life to emerge. If that possibility is ever confirmed, it would fundamentally change the understanding of life in the solar system. It would suggest that life could arise independently on multiple planetary bodies under suitable conditions. Even without confirmation, this possibility continues to shape exploration priorities. Future missions are increasingly focused not only on surface exploration, but also on subsurface investigation, sample return, and high-resolution chemical analysis. The goal is to move beyond environmental description and toward definitive answers about planetary history and biological potential. In this context, Mars represents not a destination already understood, but a layered archive of planetary evolution still being decoded. Human missions, if they occur, would represent the next stage in that process. They would not replace robotic exploration, but extend it, adding direct human observation to an already extensive dataset gathered over decades. The future of Mars exploration, therefore, is not a single event but a gradual convergence of robotic precision and human presence. Each step builds upon the previous one, extending both reach and understanding. And yet, even as plans for human arrival develop, Mars remains unchanged in its fundamental nature. it continues to orbit the Sun as it has for billions of years, carrying within its surface the records of ancient environmental transitions that predate human civilization entirely. The red planet stands at the intersection of past and future. It is a world shaped by deep time, now entering an era in which it may also become part of human time. By this stage in Mars exploration, the planet had already transformed in human understanding more than any other world beyond Earth. What began as a faint reddish point in ancient skies had become a mapped, analysed and partially traversed planetary body. Orbiters had charted its surface in global detail, landers had measured its atmosphere at ground level, rovers had crossed its terrain, and advanced missions had begun collecting samples for future return. Yet even with all of this progress, Mars remained only partially known. Its present state was increasingly well understood, but its deeper past and its long-term future still carried unanswered complexity. As scientific knowledge expanded, Mars was increasingly viewed not as a static object, but as a planet that had undergone profound transformation over billions of years. Evidence from multiple missions suggested that it had once possessed a thicker atmosphere, a warmer climate and stable bodies of liquid water. Rivers had carved channels across its surface, lakes had formed in basins like Jezero Crater, and sediments had accumulated in layers that now preserve a record of ancient environmental conditions. This ancient Mars was not speculative in the way early telescopic interpretations had been. It was reconstructed through geological evidence, mineral analysis, and orbital mapping. While many details remained uncertain, the overall picture of a wetter early Mars had become one of the strongest conclusions in planetary science. The question that naturally followed was not only what Mars had been, but what it had become, and why. One of the leading explanations for Mars's transformation involves atmospheric loss. Unlike Earth, Mars does not possess a strong global magnetic field today. This absence means that solar wind, streams of charged particles emitted by the Sun, can interact directly with the upper atmosphere. Over long periods, this interaction is believed to have gradually stripped away much of Mars' original atmosphere. As atmospheric density decreased, surface pressure dropped. With lower pressure, liquid water became unstable on the surface, either freezing or sublimating directly into vapour. Without stable liquid water, the planet's climate shifted toward increasing dryness and temperature extremes. Volcanic activity, once significant in Mars' early history, also declined over time. As internal heat decreased, geological activity slowed, reducing the planet's ability to replenish atmospheric gases. Combined with atmospheric loss, this contributed to the long-term transition from a potentially habitable environment to the cold, thin atmosphere world observed today. Despite this transformation, Mars did not become entirely inactive. Even in its present state, it retains seasonal processes, dust circulation, polar ice cycles, and atmospheric chemistry variations. The planet continues to respond to solar energy, even if in a limited and attenuated form. As exploration continued, attention increasingly turned toward the possibility that some record of ancient habitability might still exist in preserved form. Subsurface environments, shielded from radiation and temperature extremes, became a key area of interest. If microbial life ever emerged on Mars, such environments would be among the most likely places for traces to remain. This scientific direction reflects a broader shift in planetary exploration, from surface observation to layered investigation. Instead of focusing solely on what is visible, missions now consider what may be hidden beneath the surface or preserved within mineral structures. At the same time, the future of Mars began to be discussed in terms that extended beyond scientific inquiry alone. Concepts such as long-term human presence, planetary infrastructure, and even large-scale environmental modification entered scientific and engineering discourse. One of the most discussed long-term ideas is terraforming, the theoretical process of modifying a planet's environment to make it more Earth-like. In the context of Mars, this would involve increasing atmospheric pressure, raising temperatures, and potentially enabling stable liquid water on the surface once again. However, current scientific understanding places such ideas far beyond present capability. Mars lacks sufficient accessible volatile materials to easily rebuild a thick atmosphere, and the energy required to modify a planetary climate is enormous. Any such process would likely require centuries or millennia of sustained technological intervention, if it is possible at all. More immediate concepts focus instead on localized habitation. Rather than transforming the entire planet, future human activity may involve constructing sealed environments, domes, underground habitats, or pressurized structures that protect humans from the external environment while allowing controlled use of Martian resources. These habitats would exist as isolated pockets of Earth-like conditions within a largely unchanged planetary landscape. In parallel, robotic exploration continues to expand understanding of Mars in preparation for these possibilities. Sample return missions, high-resolution subsurface radar mapping, and advanced atmospheric studies are all designed to refine knowledge of the planet before any sustained human presence begins. One of the most significant aspects of current exploration is the growing ability to reconstruct environmental history in detail. Each rover, each orbiter, and each lander contributes to a layered data set that allows scientists to reconstruct how Mars evolved over time, from a potentially warmer and wetter world to its present state. This reconstruction is not only scientific but also temporal. Mars is effectively a preserved record of planetary evolution, frozen in different stages across its surface. Ancient river valleys remain visible, sedimentary layers preserve water interactions, volcanic structures record internal geological processes. Even atmospheric changes are encoded in mineral formations and surface chemistry. In this sense, Mars functions as a planetary archive. Looking forward, the next phase of exploration will likely involve deeper integration of surface and subsurface investigation. Missions will target regions where water ice is accessible beneath the surface, where organic molecules may be preserved, and where geological formations can provide clearer insight into ancient environmental conditions. At the same time, the possibility of human presence introduces an entirely new dimension. Human explorers would not only analyse Mars but experience it directly, adding sensory and observational perspectives that robotic systems cannot replicate. However, this presence would also require careful management to avoid contamination of environments that may still hold scientific significance. Mars, therefore, exists at a unique intersection in its long history. It is no longer a distant unknown, yet it is not a fully integrated part of human civilization. It is a neighbouring world in transition, not in its physical state, but in its relationship to humanity. As the solar system continues its slow evolution, Mars will remain a stable planetary body orbiting the Sun. Its surface will continue to be shaped by dust, wind, and occasional atmospheric changes. Its polar ice will continue to cycle with seasons, and beneath its surface, chemical and geological processes will continue at slow, almost imperceptible rates. But from the perspective of human history, Mars is entering a new phase, one defined not by observation alone, but by interaction, exploration, and potential presence. Whether it becomes a future habitat, a preserved scientific site, or simply a long-term outpost of robotic investigation, remains uncertain. What is clear is that Mars has already changed its role in human understanding. It is no longer just a planet to be studied from afar. It has become a world that is increasingly known, increasingly reachable, and increasingly part of the broader story of life's search for context in the universe. And as exploration continues, Mars remains exactly what it has always been in its deepest sense, a second world, slowly revealing its history layer by layer, waiting for the next stage of discovery to unfold. Long after the first waves of robotic exploration and early concepts of human arrival, Mars had already settled into a permanent place within human understanding. It was no longer treated as a temporary focus of scientific curiosity or a distant target of exploration campaigns. Instead, it had become a continuous presence in how humanity interpreted its own place in the solar system. Every generation that studied Mars added a new layer of meaning to it. For early astronomers, it had been a shifting point of light with mysterious surface markings that invited speculation. For the first space-age missions, it became a harsh, cratered world revealed through grainy images transmitted across millions of kilometers. For landers and rovers, it became a physical surface that could be touched, measured, and analysed. And for modern missions, it became a geological archive, preserving the history of planetary transformation across billions of years. Yet even as scientific understanding deepened, Mars also became something else, something less measurable. It became a reference point for imagination, planning, and long-term thinking about humanity beyond Earth. This transformation did not come from a single discovery or mission. It emerged gradually as each new data set from orbiters, landers, and rovers added complexity to the picture. Mars was repeatedly redefined, not because earlier interpretations were entirely wrong, but because each new layer of information revealed that the planet was more dynamic, more varied, and more historically rich than previously understood. What began as a seemingly simple question, whether Mars was Earth-like or not, evolved into a much broader inquiry into planetary evolution itself. Mars became a case study in how planets change over time when atmospheric, geological, and magnetic conditions shift. The loss of its thick atmosphere, the fading of its magnetic protection, and the cooling of its interior all contributed to a long transition from a wetter ancient world to a cold and thin atmosphere environment. This transformation did not occur suddenly, but unfolded over immense timescales, leaving behind overlapping geological signatures that can still be read today. In this way, Mars functions almost like a preserved timeline. Each region of its surface represents a different chapter in planetary history. Some areas preserve evidence of ancient rivers and lake beds, others record volcanic activity, and still others reflect the long period of atmospheric erosion and surface oxidation that defines the planet today. Even the dust that constantly moves across its surface is part of this ongoing story. It reshapes the landscape slowly, but continuously, redistributing fine particles across vast regions and partially obscuring older formations while revealing new ones beneath shifting layers. Despite this constant change, Mars remains fundamentally stable as a planetary body. It continues its orbit around the Sun, maintaining predictable seasonal cycles and daily rhythms. Its axial tilt produces variations in climates similar in structure, though not in intensity to those on Earth. Its polar caps expand and recede, its atmosphere expands slightly in warmer seasons, and its surface responds subtly to solar influence. These processes, while modest compared to Earth, give Mars a sense of continuity rather than stagnation. In the context of human exploration, Mars has also become a long-term planning horizon. Missions to the planet are no longer viewed as isolated achievements, but as steps in a continuous sequence of development. Each rover, orbiter, and lander contributes not only to immediate scientific goals, but also to the infrastructure of future exploration. Data from past missions informs landing site selection for future ones. Geological findings guide sample collection strategies. Atmospheric measurements help refine entry and descent systems. Even small discoveries, such as variations in soil chemistry or unexpected mineral formations, become part of a growing database that shapes how humanity approaches the planet. In this sense, Mars exploration is cumulative rather than linear. Each mission builds upon the previous one, extending understanding incrementally rather than replacing it. As technological capability increases, the scope of possible exploration also expands. High-resolution imaging from orbit now allows scientists to identify surface features at extremely fine scales. Rovers can analyse rocks at microscopic levels. Planned sample return missions aim to bring fragments of Mars directly to Earth-based laboratories, where they can be studied with instruments far more advanced than anything that can currently be deployed on another planet. These developments represent a gradual shift from remote observation to direct material analysis. Mars is no longer only seen, it is increasingly being physically examined in ways that bridge the distance between planets. At the same time, the idea of human presence continues to exist as a long-term possibility, not as an immediate expansion, but as a distant extension of current capabilities. If it occurs, it will likely begin not as a permanent settlement, but as a series of carefully controlled missions, each building on the success of the previous one. Such missions would not only explore Mars, but also redefine the relationship between Earth and other planets. They would represent a shift from observation to participation in another planetary environment. However, even without human arrival, Mars continues to evolve as a scientific and conceptual presence. It remains a focal point for studying planetary formation, atmospheric loss, climate transition, and potential habitability beyond Earth. Perhaps most significantly, Mars has become a reminder of planetary fragility and transformation. It demonstrates that a world can once have conditions very different from its present state, shaped by internal and external forces over vast spans of time. It shows that habitability is not a fixed condition, but a changing one, dependent on multiple interacting systems. In this way, Mars reflects not only its own history, but also provides context for understanding Earth's long-term planetary evolution. As exploration continues, Mars will likely remain in this dual role, both a subject of scientific investigation and a mirror for broader questions about planetary change, life, and time. Its surface will continue to be studied in increasing detail. Its subsurface may eventually reveal deeper chemical or biological clues. Its atmosphere will continue to be monitored for subtle variations, and its geological record will remain one of the most complete archives of planetary evolution accessible to human science. Yet despite all of this, Mars will still retain a sense of distance. It will remain another world, reachable in theory, partially known in practice, and still holding unanswered questions beneath its surface. And so Mars continues in its quiet orbit, neither fully understood nor entirely unknown, existing as a steady presence in the solar system and in human thought. A planet that has moved from myth to measurement, from observation to interaction, and from mystery to layered understanding, without ever fully losing its sense of the unknown. For most of human history studying Mars, attention was naturally drawn to its surface. The red deserts, the vast canyon systems, the towering volcanoes, and the dry channels of ancient rivers all formed the visible identity of the planet. Every major mission, from early orbiters to advanced rovers, had focused on this outer layer because it was the most accessible and immediately revealing. But as exploration matured, a quiet realization began to take hold across planetary science. The surface of Mars might not be the whole story. In fact, it might only be a thin outer skin covering a far more complex hidden environment beneath. This idea did not emerge suddenly. It developed gradually from multiple lines of evidence gathered over decades. Orbital radar instruments detected anomalies beneath the surface, suggesting layered structures that extended deeper than expected. Rover data hinted at minerals that formed in the presence of water, under conditions that likely existed below ground rather than at the exposed surface. Even atmospheric observations contributed indirectly, as they revealed processes that could not fully explain certain chemical signatures without subsurface interaction. Over time, these separate clues converged into a single increasingly important concept. Mars may still contain a protected subsurface environment, largely shielded from the harsh conditions of the surface. Unlike Earth, Mars does not have a strong global magnetic field to deflect cosmic radiation. As a result, the surface is continuously exposed to high-energy particles from space and from the Sun. Over long periods, this radiation breaks down organic molecules and alters surface chemistry. Combined with extreme temperature fluctuations and a thin atmosphere, the surface becomes a highly hostile environment for long-term chemical stability. However, just a few meters below the surface, conditions begin to change. Radiation exposure drops significantly with depth. Temperature variations become more stable. Ice deposits remain protected from sublimation. Chemical environments become less oxidized and more isolated from direct atmospheric interaction. In some regions, subsurface ice has been confirmed, indicating that water is not only a feature of Mars' past, but also a current, preserved resource beneath its surface. This hidden layer fundamentally changes how Mars is understood. It means that while the surface appears cold, dry, and inactive, the subsurface may preserve conditions that are chemically more stable and potentially more relevant to questions of past habitability. If microbial life ever existed on Mars, the subsurface is one of the most likely places it could have survived, especially during the planet's transition from a wetter ancient climate to its present arid state. This possibility has shifted exploration priorities in subtle but important ways. Instead of focusing only on surface features, modern missions increasingly consider what lies beneath. Instruments capable of ground-penetrating radar mapping have been deployed from orbit. Rovers analyse soil composition not just at exposed rock faces, but also in drilled samples taken below the surface crust. Even recent rover systems have begun incorporating drilling tools designed specifically to access subsurface materials. These tools allow scientists to bypass the most radiation-altered upper layer of soil and reach deeper regions where chemical signatures may be better preserved. One of the most significant findings supporting the subsurface hypothesis is the detection of large ice deposits beneath mid-latitude regions of Mars. These deposits are not only frozen water, but also potential records of past environmental conditions. Trapped within them may be dust, gas bubbles, and chemical traces from different periods of Martian climate history. In some interpretations, these subsurface ice layers function like time capsules, preserving snapshots of Mars at different stages of its evolution. The existence of subsurface water ice also has implications for future human exploration. Water is not only essential for survival, but also a key resource for fuel production and oxygen generation. If accessible, these ice reserves could significantly reduce the need to transport resources from Earth, enabling more sustainable long-term missions. However, accessing these resources is not simple. The subsurface environment of Mars is difficult to reach, and even more difficult to operate within. Drilling systems must be lightweight, yet capable of penetrating solid regolith and ice-rich layers. Equipment must function in extremely low temperatures, and any interaction with subsurface materials must be carefully managed to avoid contamination of environments that may hold scientific significance. This introduces another important concept in Mars exploration: planetary protection. As exploration extends deeper beneath the surface, scientists must ensure that Earth-based organisms do not inadvertently contaminate potentially sensitive Martian environments. This concern is especially important in regions where liquid water may exist temporarily, or where chemical conditions could support microbial activity. As a result, subsurface exploration is governed by strict procedural limits, balancing scientific curiosity with environmental caution. Despite these challenges, interest in the subsurface continues to grow. It represents one of the last major frontiers of Mars exploration that remains largely untouched. While the surface has been mapped, analysed, and traversed in multiple regions, the subsurface remains only partially understood, inferred primarily through indirect measurements. Future missions are increasingly designed with this hidden layer in mind. Advanced landers and rovers are being developed with deeper drilling capabilities, improved subsurface imaging systems, and more sensitive chemical detection instruments. Some proposed missions even envision autonomous subsurface probes capable of entering ice-rich regions to study internal structures directly. At the same time, orbital missions continue to refine global maps of subsurface composition, identifying regions where ice, minerals, or layered deposits may be most accessible. As knowledge grows, the distinction between surface and subsurface Mars becomes more significant. The surface represents the current state of the planet, cold, dry, and shaped by wind and dust. The subsurface represents continuity with the past, protected layers that may preserve ancient environmental conditions and possibly even biological signatures. Together they form a dual structure, one visible and active in a limited sense, the other hidden and potentially ancient in preservation. This duality reinforces a broader theme that has emerged throughout Mars exploration. The planet is not defined by a single condition, but by multiple overlapping states across time and depth. Its surface reflects present-day processes, while its subsurface may preserve earlier eras in suspended form. In this way, Mars is not only a planet of history but a planet of layers, each one representing a different stage of transformation, each one contributing to a larger planetary narrative. And as exploration continues, it becomes increasingly clear that understanding Mars fully will require not only looking across its surface, but also beneath it, into the quiet, hidden regions where time itself appears to be preserved in frozen and mineral form. Across billions of years, Mars has moved through transformations so vast that they are almost difficult to place within a single narrative. It formed alongside the rest of the solar system from the same primordial material, gradually coalescing into a distinct planetary body shaped by gravity, heat, and time. In its earliest known history, it likely shared many characteristics with other young terrestrial worlds: volcanic activity, a thicker atmosphere, and conditions that may have supported flowing water across its surface. Over time, however, Mars followed a different evolutionary path. Its internal heat slowly diminished, its magnetic protection weakened, and its atmosphere gradually thinned. As these changes unfolded over immense timescales, surface water became unstable and eventually disappeared from the open landscape. Rivers dried, lakes vanished, and the once active hydrological cycle faded into geological memory. What remained was a cold, arid world shaped primarily by wind, dust, and slow atmospheric processes. Yet Mars never became truly silent. Even in its present state, it continues to change in subtle ways. Dust storms travel across its surface, sometimes expanding to planetary scale. Seasons bring shifts in temperature and atmospheric density. Polar ice grows and recedes in rhythmic cycles. Beneath the surface, ice deposits remain preserved, and chemical processes continue at slow, almost imperceptible rates. Mars is not a static planet. It is a planet in slow motion. Human exploration has revealed this reality layer by layer. Early telescopic observations introduced its visible features. Spacecraft flybys confirmed its cratered surface. Orbiters mapped its geography in detail. Landers touched its ground for the first time. Rovers travelled across its terrain, extending understanding beyond fixed points. And modern missions now study its history in unprecedented resolution, analysing ancient lake beds, river deltas, mineral formations, and atmospheric changes. Each mission has not replaced the previous understanding of Mars, but expanded it. With every stage of exploration, Mars has become more complex, not less. Instead of resolving into a simple answer, it has unfolded into a layered system of history, each layer representing a different environmental era. A wetter ancient Mars, a transitional Mars, and the cold desert world seen today are not separate interpretations, but connected phases of a single planetary evolution. At the same time, Mars has become more than a subject of science alone. It has become a reference point for long-term thinking about life, planetary change, and the future of exploration. It represents a world that is close enough to study in detail, yet distant enough to remain fundamentally separate from Earth. A world that invites questions about habitability, survival, and transformation across deep time. Even now, with advanced rovers analysing ancient sediments and orbiters scanning for subsurface ice, the most important questions remain open. Whether Mars ever hosted life, whether it still preserves hidden environments capable of supporting it, and what its full geological history ultimately reveals are questions that continue to guide exploration forward. And perhaps that is what defines Mars most clearly in the present moment. It is not a world of final answers, but a world of continuing discovery. A planet that has shifted from myth to measurement, from observation to interaction, and from distant mystery to layered understanding, without ever losing its depth of unknown. As future missions prepare to return samples, send humans closer, and explore beneath its surface, Mars remains in the same quiet state it has held for billions of years, orbiting the Sun in steady rhythm. Waiting, not passively, but simply as a world that still holds more history than has yet been read. And in that sense, Mars continues to exist not only as a planet in space, but as an unfolding story in time, one that humanity has only just begun to understand.